Like you can't make the assumption that just because we know retina, fiber, that explanation will be isomorphic to how it works everywhere else, where it's completely shrouded in mystery and we have no idea how thoughts and the subjective experience map onto the physical.
You are tuning in to The Multiversity, a podcast for higher dimensional education.
Join us as we explore philosophy, science, history, and the great unknown.
So, okay, that's one interpretation. Another interpretation, and I'm not a physicist, but the way that I would think about this, if I were going to go down a many worlds train of thought, is there's lots of teeny tiny things happening within our own minds all the time, and our mind, our consciousness is like observing itself all the time, right? So would it be a reasonable interpretation that, like, within our own minds, we're constantly bifurcating things by observing what's going on within ourselves?
Well, yeah, I mean, this sort of bifurcation only happens when one system is interacting with another system, which is in superposition. So, the brain is kind of a very kind of like warm object where things are not well isolated, and it's sort of hard to believe that kind of the sort of somewhat more macroscopic structures that are actually involved in thought, if we're talking about neurons and axons and dendrites and things you can see under a microscope. The actions, the things that are going on there to carry presumably to carry thought, those are not things that are happening in quantum superposition. Those are things that you can look at. You can stick electrodes in someone's head and read out what's going on.
But I don't know. I mean, they found quantum effects with buckyballs. Buckyballs are far larger than neurotransmitters. And from what the little I've studied of this, they've found quantum effects taking place in, like Chris mentioned yesterday, like living tissue, proteins, the way that proteins fold, there's a quantum element.
Yeah, apparently photosynthesis involves some kind of quantum transfer of energy.
Well, sure. It all depends on what exactly you mean and what is meant by quantum in that case. I mean, of course, we're talking about sort of biochemistry now. So at the level of chemistry, chemistry is explained by quantum mechanics. So all chemical effects are quantum mechanical effects, and all molecules individually obey the rules of quantum mechanics. Now, if we're talking about the operation of the brain in particular, it's not. I don't think it's generally believed that individual neurotransmitter molecules are orchestrating thoughts sort of on that microscopic scale at the level of chemistry and at the level of quantum chemistry. It's normally believed that that's done by neurons, and they fire these action potentials, which you can read out in a very coarse sense.
Okay, now this is a thing that I know about to some extent. The brain is an electrochemical machine. That's one way of thinking about it, at least. So the brain is an electrochemical system. So you have like the action potential traveling through a neuron, but at the end of the neuron, it releases a neurotransmitter that then diffuses through the synapse to the next neuron. So the way the signal works is it's like electrical, chemical, electrical, chemical, electrical, chemical. And it's often interpreted in a Newtonian way. Like that's the paradigm that we're on. It's like if you're depressed, we'll just put some more dopamine in and then you'll be less depressed. And that system works to a certain extent, but it works very imperfectly. And our knowledge of the brain is very, very limited, very imperfect, particularly when it comes to some of these issues that Katie brought up, like choice, consciousness, stuff like that, free will. We do not have a scientific explanation for these phenomenon. And I guess what I'm trying to point out is we don't know. Like, we don't know to what extent, we don't know to what extent quantum phenomena like impinge on the functioning of the brain. We do seem to know that there's some element of quantum physics does impinge on like protein folding and photosynthesis. So it's not entirely like quantum biology is like an emerging field, but there definitely are structures in the brain that are small enough. Like that's undeniable.
Well, everything is I mean, there were a lot of things you got into there, but let me just say, I mean, everything is made of molecules. So, everything has a length scale on which, quantum effects happen. And, you can't understand what's going on without following the laws of quantum mechanics. That said, to my knowledge, there's no indication whatsoever that those quantum effects are important in the actual operation of the brain.
So just back up a little. There's actually, if you Google quantum photosynthesis, experiments confirm superpositions occur in light harvesting bacteria. And that basically just, you were saying, I kind of highly doubt that there are these quantum superpositions happening in the brain because it's this, warm, chaotic environment. But yeah, apparently there's.
So I mean, we're jumping between totally different.
Yes. When it comes to the brain, though, like you say, there's no indication. But I mean, our knowledge of consciousness is like 15th century. Like in the 15th century, I could have said there's no indication that. Pick any modern scientific. There's no indication that tiny invisible creatures make us sick. Like you could have said there's no indication. Like when your knowledge of something is very primitive, you can say that there's no clear path to the solution, but there's no indication also that quantum phenomenon are completely irrelevant when studying the function of the brain. And there are like specific instances where we can think of where very small molecules are acting in some degree of isolation, like when they're diffusing through the synapse.
Well, I mean, I probably have to say here, I'm not a neuroscientist. I'm not a lot of things, it turns out. But I don't think it's the case that we know so little about the brain that we could say, it could very well be that thoughts exist in quantum superpositions. We've intensively studied nervous systems, and we know quite a number of things. My specialty in computer science is in computer vision, so I know a little bit about what people know about the visual system, and we know very definitive things about how light impacts the retina and how that gets translated into these electrochemical signals. Which pass along neurons, and you can stick electrons in. It's usually cats, but you can stick electrons in any nervous system and measure these signals, and you can make sense of them. I mean, you can see, okay, light hitting the retina has this pattern. That's what lights up this neuron. And sure, you can go to other parts of the brain and say, well, I don't really know what this neuron does. I don't understand it, and there's no global theory of like how do we actually come up with thoughts, and how does our global perception of ourselves sort of arise out of that. There's a lot unexplained. But on the sort of microbiology level of how do individual neurons work, I'm, at least personally, I'm pretty convinced that the output of a neuron doesn't depend on some kind of quantum superposition.
Well, no, but you're talking about, you're focusing a lot on the level of the neuron, which makes sense because if you're looking at computer vision, there's a lot of very long neurons transferring electrical signals long distances there. So, which is a more Newtonian process. Like I'm not really contesting the idea that what happens within a neuron is pretty Newtonian. What I'm saying is, for me, from what my limited knowledge of this, it does seem like what happens between neurons is happening at a scale below what we've observed quantum phenomenon at. So it doesn't seem completely crazy to me that stuff there, that there could be some quantum effects happening there.
I'm including in this, what is happening between neurons. It's certainly the case that we can, grow a small collection of neurons, in a petri dish or wherever you grow neurons, and see that, when the outputs of these neurons fire in a certain way, you can see the output of the neuron that's connected up fires in a way that you can model. And, it's not, those models have a certain level of precision, and it's not, this field of study is not complete But how neurons communicate, I think, is pretty well understood. At least on the basic level of sort of how thinking gets done. And I mean, if
no, but they don't know how it maps onto thinking at all. Like they know some things like how the light signal passes from the retina to the occipital lobe, but again, that's a process where you mostly have nerves just bringing the signal back. There's no synapses in that process, and then once it gets there, oh, now it's a total mystery for the whole rest of the brain. Like you can't make the assumption that just because we know retina fiber that explanation will be isomorphic to how it works everywhere else, where it's completely shrouded in mystery and we have no idea how thoughts and the subjective experience map onto the physical.
Well, thinking may have been too strong or too vague of a word, but it's not the case that it's simply the neurons in the retina and we look at the outputs of those and we see, oh, those correspond to the inputs. I mean, people go beyond that into the visual cortex and say, okay, there's a layer called V1, there's something called LGN in between that, and these things are connected up in layers, and you can go and see higher layers of structure. You can see, okay, this thing responds to certain patterns where things in the visual field have a certain angle, and this one responds to blue dots in a certain location, and then and you can see that they're all arranged in a certain way that kind of makes sense. Sort of anatomically to sort of represent the whole visual field. So I mean, there has been a lot of study in this field, and there's a lot that's still to be explained, but there's a lot that has been explained, and there's nowhere in those explanations does quantum superposition enter into this.
No, but I mean, those explanations are incomplete and we don't know what's going to be required to complete them. And I mean, those kinds of explanations that you're talking about, like regional explanations and like single neuron explanations, like they work pretty well for something like the visual cortex, even though those explanations still run into problems there. But like, you don't actually have a neuron for blue. Like you don't actually have, like, you have a very limited number of neurons. Like it's not like there's one neuron for each thought you have, or one section of the brain for each thing you do. It's much more complicated than that. And like the cutting edge view of how the brain works now is that it's network effects. Like that's the current paradigm. Not like they started with single neurons and they're like, oh, what we can explain with single neurons is actually extremely limited. Well, maybe it's brain sections. And then they sectioned off the whole thing and they were like, this gives us some information, but it's very imperfect. It's very imperfect and doesn't seem to map well onto how thought works at all. It's like, it's like taking a 15th century. It's like, that's why I say it's 15th century. It's like you take a 15th century map of the world, and it's like, Europe is this giant thing, and there's dragons on this side, and I don't know. They kind of know that India exists, and they're like, see, look how well we've mapped the world. There's not much more to know, but that's exactly what we have of the brain. It's like a 15th century map, and
sure. I mean, your point is well taken. It's certainly true that we do not have a global theory of what the brain is doing, and there's a lot unexplained about the brain. But we're sort of, when you say, well, we understand individual neurons, but we don't understand really what collections of neurons do together, it's true. But it seems like we're going in the wrong direction to bring quantum mechanics into this.
I'm not saying we should necessarily bring quantum mechanics into this. Like, I'm not writing a research paper. I'm just saying I think discounting it is also, especially when the issue that caught us into this is when Katie brought up the idea of like choice and consciousness and free will, which are issues that are still very much in the realm of philosophy, which tends to occur when science in a particular area is at a primitive position, as it is in this case.
Yeah, I think what I'm trying to say is that I mean, it's not really that there's something unexplained and it might be quantum mechanics. It's that there's something unexplained and there's sort of no way to imagine that it could possibly be quantum mechanics.
We don't have any way of understanding how the brain itself as a physical object gives rise to a subjective experience. We don't have any mechanism for that. Everything that we understand about the brain could work. Everything that we understand it's so Newtonian that you could do it. You could just program a machine to do it that doesn't have subjectivity, and it could do it. Like, I'm not saying that everything, I'm not making the claim that everything the brain does could be done by a machine, but everything that we currently thoroughly understand about what the brain does can be mapped by a machine that doesn't have subjectivity. So clearly we haven't found that mechanism that produces subjectivity, and which is why I think it's fair to be more speculative about it, because we really don't understand anything. We're only looking at a 15th century map.
I mean, we're getting a whole other topic here. We have to say, what we mean by subjectivity, but, I'll just say, my job is to program computers to do things that the brain does. And not, my job is not to emulate the brain. It's just to solve similar problems.
Exactly. That's what I'm saying. The things that we can get computers to do that the brain also does, like we're getting pretty good at computer vision, pick your poison, whatever, you say computer vision. We have a certain understanding of the visual cortex, understand how it does certain things. And we can get the computer to do certain things. We can now get it to recognize objects pretty well and stuff like that, and to see outlines that things it couldn't do before. But all those things are possible to be done without subjectivity, is what I'm saying. We can't make a robot that is conscious, because we don't understand consciousness at all. We're not even close to understanding it. We're so far away from understanding it that many neurologists still would rather not even discuss it.
Well, sure. I mean, this no longer seems to be about quantum mechanics per se, but if you want to say we can't make a robot that's conscious, but you also want to say we don't know what consciousness is, then it seems hard to defend that claim.
Well, I'm making the claim that I'm making the claim at the current time our knowledge of consciousness is so limited that we can't emulate it in any way, and we can't explain it. Anyway, go ahead, Chris.
Yeah, so I just wanted to point out maybe a couple of places where you guys might be talking past each other. John, you are talking about vision and, and how, computer vision maps onto the visual cortex and how that process is fairly deterministic and there isn't anything spooky that's happening. And Ariel is talking about how, no, there isn't anything spooky happening in vision, but maybe there's something spooky happening in subjective experience. And maybe there's something going on in that process, which involves something, strange or quantum. I'm also wondering, Ariel, are you trying to suggest that maybe the brain is some kind of quantum computer?
I think I would have to know more about quantum computers to answer that question. I guess the point I was trying to make at a deeper level is I don't think it's a convincing argument to say everything we understand about the brain is Newtonian and non-spooky, therefore the whole brain is Newtonian and non-spooky, because it could just be that because the way that we're choosing to look at the brain, which is basically as a machine, is limiting our ability to understand the spookier parts of it.
It's also very difficult for us to understand spooky parts or know where to start with trying to study spooky parts. So, I mean, it makes sense that everything that we would understand would be the stuff that's easy to understand, right?
Yeah, I think I agree with the way the argument's been laid out there. I think the thing I would add to that is that the things we do understand about the brain are on a level which sort of I would say convincingly screams out quantum mechanical effects.
So, okay, let me flip the original question around and come at it from a different angle. Well, not really a question, but let me just go this direction. We're talking about the many worlds interpretation. We're talking about an interpretation which, it's just a possible interpretation where the observer bifurcates reality. So if we were to go with that interpretation, and you are the observer, would that philosophically make sense, or how would it make sense for you to have an observer that bifurcates reality, but there's nothing going on within the observer at the quantum level that's spooky?
Well, so it's not that the observer bifurcates reality. The observer doesn't have the responsibility here. It's merely that reality bifurcates because that is what the laws of quantum mechanics say. And
the reality bifurcates and the observer shows up in two places.
Reality bifurcates is again kind of a sensationalistic way to say it. What happens is, indeed, the observer shows up in two places.
So there's something special about the observer. Maybe it's not the observer's responsibility, but reality is bifurcating, and the difference between the two realities is that there's two different observers. Thank you for joining us on the Multiversity. We hope you found this episode both mind-bending and enjoyable.
We can be found all over the social media space and at multiversitypodcast.com.
If you like this content, give us a like, comment, follow, share, or support us on Patreon.
Catch you on the flip side.